Hi everyone, so today we will be learning about enthalpy change. So in your module, you can read this as the term enthalpy, represented by the symbol H, is from the Greek word meaning enthalphen, meaning to warm. It refers to the energy transferred under constant pressure. So the constant here is pressure. So it refers to the energy transferred under constant pressure, not constant temperature or whatsoever. It's constant pressure. So enthalpy is often referred to as heat content. So for reactions that occur in an open container at constant pressure, the delta H, when we say delta H, it refers to the change in H. Change in, when we have this symbol triangle, we are referring to a change that is happening. So delta H is equal to the difference of in enthalpy between final and initial states of the system, as given by this equation. So when we have change in enthalpy, we're referring to the difference between the final H and initial H. So H is the heat. So enthalpy change, delta H, that accompanies the chemical reaction is called the heat of reaction. So we usually see enthalpy change as a reaction A plus B, C, then we have a change here. We have something in the right side. Let's just say that it's delta H 90.1 kilojoule. So this is how we usually see enthalpy change. The left side is a chemical equation, reaction, and the energy needed or heat content is written in the right side. Okay, that's how you write a chemical reaction. It should be with the heat required, or the heat content, the enthalpy change. The enthalpy change required for this reaction to happen. So this is the net energy change resulting from breaking and the making of bonds. So we know that in a reaction, we follow a conservation of mass, meaning the mass in the products is equal to the mass of the reactant. But the new bonds are formed and the old bonds break. So that's how what we learned on what happens during a chemical reaction. So it represents heat absorbed or evolved when the reactants are converted into products at constant pressure. Never forget that the change in enthalpy is always during at constant pressure. So it represents the heat absorbed or evolved when the reactants are converted into products at constant pressure. So this is how you equate it. So delta H is equal to H products minus H reactant. So at constant pressure, delta H is equal to Q. Okay, so Q here is actually the heat. It's the actual heat. It's the heat transferred or evolved, right? So the sign of delta H indicates the direction of heat transfer. So in an endothermic process, I hope you're already familiar with endothermic and exothermic processes. So endothermic process, the Q here is equal to the delta H greater than 0. So the heat content in product is greater than in reactant. While exothermic process, the heat content in products is less than the heat content of the reactants. So this is found in your module. So when we have a surroundings, it's anything from the universe, and the system is found within the surroundings. So the heat is absorbed in the system. We have delta H should be greater than 0 when we have an endothermic process. The heat is absorbed, while in exothermic process, the heat is released from the system to the surroundings. So again, in endothermic, the heat from the surroundings is absorbed to the system, and delta H, the enthalpy change is greater than 0. While in the surroundings, the heat is released from the system to the surroundings, and the delta H, or the heat content, the enthalpy change is less than 0. So that's how we differentiate between endothermic and exothermic processes. So to really understand or to visualize what enthalpy change is, we have this problem here. The enthalpy change is being asked, so we use solving here. So calculate the enthalpy change for the following chemical reaction. We have the CS2 liquid plus the 3 moles of oxygen gas. It produces CO2 gas and SO2 gas. Sorry. So the before we jump start, we make sure that the formula, the equation is balanced. So this one is a balanced equation. We have 1 mole of C on both the product and reactant side, and we have 6 moles of oxygen in both product and reactant side, and 2 moles of sulfur for both product and reactant side. So we actually have this formula here. We have a formula with its corresponding enthalpy change. So we name this formula as 1, 2, 3. Okay, so we need to solve using this given and come up with this one. So how do we do that? So first, let's look at the product side. Okay, so I think I would go with, first I want to have C and S, carbon, sulfur, and oxygen in my product side. So we know, reactant side. We have reactant and product. So in our reactant side, we want these elements here, right? And in our product, we actually want to have these compounds or elements here. We have CS2 and O2. In our product, we want CO2 and SO2. So from the given formula, we look at that the CS here is in equation 3 and it's in the product side. So we rewrite equation 3 as CS2 C plus 2S. And don't forget the enthalpy change on the right side. So since we transpose this one from product to reactant, we also multiply the enthalpy change to negative. So we have 87.9 kg, and it is negative. It is now negative since we transfer the CS2 in our reactant side, and the products, in the and the reactants C and 2S are transferred in the product side. So we have this new equation here. We used equation 3 for this. So this is where we start. And then we want to have O2. Okay? So by trial and error, I think I have to go with the second equation here. We have S plus O2 SO2. And I noticed that this equation 2, is not balanced yet. So this one is not balanced. So I'd like to, no, it's actually balanced, but I want to have an O2 with 3 coefficient here. I want to have the oxygen to have a coefficient of 3. So that's for later part. So I'll just first write the enthalpy change required, which is in equation 2. It's negative 296.8 kg. And I'll write the first equation na lang. First, we have C plus O2 and CO2. And also write the enthalpy change. We have negative 393.5 kg. So we take the sum for this, and again we want to arrive with this final equation here, CS2 3O2. Okay, so let's first make some adjustments. For this to have a 3O2, we want to multiply this by 2. This one, we want to multiply this by 2. And in order to have a balanced equation, we multiply all components by 2, including the enthalpy change. So now we have this one. Okay, so instead of having negative 296.8, we now have negative 593.6 kg. So this is our new value for the second equation. Then we add the formula here. So now we have CS2, and now we have 3O2. So 2 plus 1, this is 1. And notice that we can cancel 2s in the product side of the third equation and the first one in the second equation on the reactant side. We can actually cancel common terms if they are in the opposite direction. If the first one is in product and the second term is in reactant. Okay, so we do not have 2s anymore. We also do not have C. since C in the third equation is in the product, and in the first equation we have it on the reactant side. Now we are left with CO2 plus 2SO2, this one and this one. And we also have this one and this one on the reactant side. And if you calculate the enthalpy change for this, we have negative 1075 kilojoules. So this is what we're looking for. The enthalpy change for this given reaction. We have arrived in this reaction is negative 1075. And that's how you solve for the enthalpy change. You manipulate, balance given equations, including their enthalpy change values.